Can you hear me out in the back? Yes? Okay. So I would like to start this talk with a show of hands. So please raise your hand, those of you who have ever used a robot driver or a controller that was not written by you. Okay, so that's most of us. Those of you who have implemented a controller or a robot driver yourselves. Okay, this is great. And subject to real-time constraints. Okay, so this is more or less what I get in most places that I go. Maybe here there's a little bit more people that have written controllers themselves. So we'll come back to this later on. So this is the basic overview of the talk. We're going to start with a big picture of what is the ROS Control project, and then we're going to talk about the main components of what we call ROS Control and Friends. Hopefully we'll be able to show a quick demo and simulation, and then we're going to talk about some of the robots that are running ROS Control right now. So let's start with the big picture. So I think this is a pretty typical scenario. You have a robot, you have a piece of hardware, and then you have this application that you want to get running with your robot. So if you're using ROS, you probably want to leverage things like the navigation stack or move it, things that you don't want to rewrite. So, and you probably also have a computer that's running a simulator, like Gazebo maybe, and then you want to put your robot there, right? So the thing here is how do you make ends meet? So this talk is going to be about that. This is where ROS Control can help you. And if you're not really into writing controllers or things with real-time constraints, then it's even more meaningful. So in the context of ROS Control, it provides tools for modeling the robot in software. This would be the robot hardware there on your right, but then also controllers that actually do interesting stuff and then talk to third-party tools. So important aspects to highlight here is that this robot hardware there tries to decouple hardware access. So you don't expose how you talk to your robot. And this is really important. And also another layer of decoupling is that controllers and your robot hardware abstraction are decoupled, so you can develop them independently and in isolation. So this enables you to share and mix and match controllers. So when you want to write your robot backend, there's a possibility to leverage out of the box a simulation backend. So this is good. And then when it comes to the time for you to write your custom hardware backend for your robot, there are also tools that help making this task easier for you. When it comes to controllers, there is already a set of existing controllers that are robot agnostic, so hopefully you should be able to leverage some of those. And well, if your application requires it, there are tools that help you also implement custom controllers. There are also tools for controlling the lifecycle of your controllers. And then when it comes to third-party tools, there is out-of-the-box compatibility with certain tools like general-purpose ROS tools like visualization, TF, RQt plugins. But then there's also compatibility with the navigation stack. Here we see a diff drive robot and a biped humanoid robot. And then also motion planning with MoveIt, but then there's also other tools. And towards the end of this image, the whole idea is that what you really want to do is maximize the resources that you spend writing your actual application or your research paper, and not spend large amounts of time writing boilerplate code in the right side of the image. And another really important aspect is that ROS Control is real-time ready, in the sense that if your application has real-time constraints, then it's even hard real-time constraints, then it's fine that you use ROS Control with it. But if your application doesn't require it, then it is not imposed on you. Also, the choice of real-time operating system is entirely up to you. So, in a nutshell, the goals of the project are to lower the entry barrier for exposing hardware to ROS, to promote the reuse of control code in the same spirit that ROS has done for non-control code, at least non-real-time control code, provide a set of ready-to-use tools, and finally, to have a real-time ready implementation. A little bit of history. By the year 2009, there was the PR2 controller manager that was developed by Willow Garage, which was PR2 specific. But then it turns out that a lot of people started asking around like, well, hey, I would like to use this in my robot. So by late 2012, HideOff, in collaboration with Will Grage as well, started the ROS Control project, which by early 2013 was continued by Power Robotics and community efforts. So ROS Control is basically a robot-agnostic version of the PR2 Controller Manager. A little bit of related work to put some context. In robotics, there's quite a few component-based frameworks like Oracle's RTT, OpenRTM, YARP, and also there's a couple of projects that build upon Oracle's RTT as well. And then for computational graph models, there's Ecto, there's microblocks, but then there's also many, many non-robotics implementations, especially within the audio and graphics communities. But the thing is, and to my big surprise, considering the success that ROS has had, is that as far as I know, there is no end-to-end solution for ROS users. So what ROS Control is trying to do here is to bring standard ROS interfaces closer to the hardware, basically to push the integration effort to the driver level, to the rightmost part of the image. And so when I talk about ROS Control and friends, these are all the friends. So there's a GitHub organization that's called ROS Controls that has things from messages and action definitions that are useful in the context of control. There are tools that help you writing real-time code and controllers. And then the two at the bottom is ROS Control, which is the core framework, and ROS Controllers, which is a set of robot-agnostic controllers that are compatible with ROS Control. So with this, we can now get into the details of, first of all, how to set up a robot. So, familiar image, we're going to concentrate right now on the part that devotes to ROS Control. So we have that the robot hardware abstraction is the guy that talks to hardware. This is the one that provides resources, like joints, and it also handles resource conflicts. On the other hand, we have controllers. These guys don't talk directly to hardware, and they require resources that are provided by the hardware abstraction. So let's focus first on the hardware abstraction. We zoom in. So in ROS Control speak, we have the notion of resources, as for example, a velocity-controlled wheel. Then we have hardware interfaces, which is just a set of similar resources. And then if you pile up a bunch of interfaces, then you get a robot. Then there's these connectors here, which are ROS Control interfaces, not to be confused with typical ROS interfaces like topics or actions or services. This is not that. In the end, we're just passing pointers around. This is something that is real-time safe. So these interfaces connect with controllers, which are the guys that use them. And then at the leftmost part of the image, controllers have their interfaces, which in this time they are typically ROS interfaces, topics, actions, services. And they are custom, so your controller can expose whatever it wants. Something that is also relevant to mention is that you can have multiple controllers accessing the same interface, but in this case you can see that the two ARM controllers both use the first ARM joint. So by default there's a policy of exclusive resource ownership, so in this case you can either have one or the other, but not both running at the same time. This is enforced by ROS Control. If you want other policies, you can implement them as well. Okay, so this is really nice, but how does this, how do you ground this to doubles and floats and the actual data that you want to pass around? So this here is supposed to depict the memory layout of your raw data. So you have, these are the memory regions where you actually read and write to and from hardware. So a resource is nothing else than pointers to the raw data that add some semantics, like, okay, this is position, this is velocity, this is the name of the joint, and it belongs to a joint state interface. The idea is really simple. And when you have a resource that actually sends commands, you can only read the state, but you can also send commands. So this would be a very simple code example. If you're in the back and you cannot read the code, don't worry. It's the idea what's relevant. So you would inherit from a class that is in ROS Control. In the constructor, you would set up your robot, which is basically filling up what you see in this in the drawing. And then there's a couple of methods where you read and write, and this is what is up to you. This is where ROS Control can no longer help you. And when you read, this is where you would populate the raw data with your robot state, and then when you write, this is when you take the raw commands and send them out via CAN bus, Ethernet, EtherCAT, serial port, whatever. Within the ROS community, there are some projects that can help you out with this. There is ROS Industrial, there is ROS Serial, there is Ronix, and there's surely other custom solutions out there that you can leverage. And then if exclusive resource ownership is not good enough for you, then you can always re-implement a virtual function and do whatever you want. So there's a package called Hardware Interface that does this. It implements all the building blocks for constructing a robot hardware abstraction. It's in fact the software representation of your robot. The idea is to abstract hardware away, and this is done recapping by means of resources like actuators, joints, sensors, interfaces that are sets of similar resources, and then a robot, which is a set of interfaces. It also handles resource conflicts, and by default we have exclusive resource ownership. So out of the box we have already resources and interfaces for reading states, such as joint state, position, velocity, and effort, IMUs, and force-torque sensors. And if you also want to send commands, there are interfaces for position control joints, but also velocity and effort control joints. There are more interfaces coming up. They are in pull request states, but right now, as of today, this is what we have. So now it's worth mentioning a couple of words about the simulation backend. There's a package called Gazebo ROS Control that lives outside the ROS Controls organization. It lives inside ROS Simulation. And it's a Gazebo plugin for ROS Control. So it comes in two flavors. There's the default plugin, where it populates all the joint interfaces from the URDF by parsing transmission specification and optionally joint limits. We're going to describe these later on. And there's also a custom plugin where most of the details are up to you. So if you use the default plugin, this is basically all you have to add apart from your transmissions to have your robot showing up in Gazebo. And this is great because with this you can test ROS control without having to write any code, just setting up some configuration files. So with this, we can continue on to controllers. So this would be these guys on the left. So if we again zoom in on this image, we have the controllers, and what we're going to do is isolate one of them, the ARM controller, and then we're going to stretch it out to see more of its internals. So recapping a little bit, we have here on the right, the controller requires resources, so there you can see the ROS control interfaces, and on the left-hand side you see the controller, the controller's ROS API. But we also have, on the top, we have a plugin interface that implements the controller lifecycle. This is a very simple state machine that has two states, stopped and running, and then some transitions between the states. And then at the bottom we see the computation of the controller, which has two components, one that is real-time safe and another one that is not real-time. So let's start by taking a look at the state machine. Here there are some non-real-time operations, like load. When you load a controller, you're basically initializing the plugin. And what you want to do here is to check requisites. So for example, the existence of hardware resources. In this case, we need two joints named ARM1 and 2, and they must implement a position interface. So if your robot doesn't have that, then your controller will say, hey, I cannot work with this robot. You can also check for things like configuration. This can be like robot-wise configuration, like the robot description and the URDF, but it can also be controller-specific configuration, like ROS parameters scoped within the controller namespace. The other thing that you want to do here is to set up the ROS interfaces, how your clients will talk to the controller. And then if you want to unload your controller, then you basically just implement that in the destructor. For transitioning between the stopped and running states, we have real-time safe operations. So when you start the controller, this is what gets executed before the first controller update. And one thing that always gets done here is resource conflict handling. And this is different from what I was talking before about resource existence. By this time, the resources, you know that they exist, but what you're going to check is that, is somebody else using that resource, or is it available for me in the case of exclusive ownership? And then you can do other stuff, but a typical policy here would be semantic zero. So when you start your controller, you would do things like hold position, zero velocity, gravity compensation, whatever makes sense to your use case. And then we have the stop operation, which actually goes from running to the stop state. And here also a typical policy is to cancel goals. So if you cancel all goals, the next time you start your controller, it won't jump and resume what it was doing the last time around. The last real-time safe operation would be update, which is a real-time safe computation, which is executed periodically in the running state. And I should note that when I talk about real-time safe, it doesn't mean that whatever you put in there is going to magically be real-time safe. It's actually a requirement on the implementation. So whatever you do there has to be either real-time safe, or if you don't have real-time constraints, deterministic. And one last very important aspect is that there is another part of the computation that exists here, which is a non-real-time operation, which is what takes place inside the callbacks of your ROS interface. So this is non-real-time computation, and it's executed asynchronously. So if we sum all of this up, we have that controllers are dynamically loadable plugins that have an interface that defines a very simple state machine. This interface clearly separates the operations that are non-real-time safe from those that are required to be real-time safe. And the computation can take place in the controller update, which in this case is both periodic and real-time safe. And then you have computation in the ROS API callbacks, which is asynchronous and non-real-time safe. There's a package called Controller Toolbox, which you should be aware of because it has some tools that help out in the process of writing a controller. I guess the most used building block is the PID controller, but then there's also some other stuff. And there's a repository called ROS Controllers that has the controllers that you should go in here and see if there's something for you to use, because it has a bunch of controllers that are ready to use. So it has 3 controllers for reporting sensor state. The first one, I guess, pretty much everybody needs, which publishes the joint states topic. But then there's also similar controllers for publishing the IMU sensor or four-stroke sensor state. As general purpose controllers, there are 3 packages that implement simple single joint controllers that operate in different control spaces: position, velocity, and effort. And then there's this guy, which is called the joint trajectory controller. It's a general purpose controller in the end, but it's mostly used for manipulation because it implements the action interface that MoveIt is expecting in the default ROS bindings. Then for navigation, there's a diff drive controller, which exposes a ROS interface that is compatible with the ROS navigation stack. And for manipulation, there's a gripper action controller, which implements a single degree of freedom gripper controller. And it implements also an action that is, again, compatible with MoveIt. So with this, we can go into the last part of this section, which is the control loop. And so far we've talked about the robot hardware abstraction and about the controllers, but we have to somehow bring all of this together. So I'm going to start this part by talking about what is called the controller manager, which lives in a package with the same name. So the controller manager knows about the robot, and it also knows about the controllers, and it has 2 main purposes. One is robot resource management. So the controller manager, because it knows about resources, it can enforce the resource conflict policy, the exclusive ownership that I was talking about before. But it also takes care of controller lifecycle management because it knows about the controllers. This is the guy that transitions the controller state machine, and it also updates the controllers. I guess it's important to mention here that by design, controller updates are serialized in a single thread, and they are periodic. The controller manager has an API based on ROS services, some of which are used to step through the controller lifecycle state machine, so you can load and unload. But you can see that there is no separate start and stop services. There's this service that's called switch. So with switch, what you can do is that in the same control cycle, you can stop a set of controllers and then start another set of controllers. And this is relevant because you might be interested in doing things like you have your arm and you want to change the controller that is running on the arm. So if you stop and then some control cycles pass until you start the next controller, what might happen is that maybe your arm starts to fall. So with this, you can guarantee that there won't be any control cycle without any controller running, unless that's what you really want to do. Then there's some other services for querying which controllers are running or not, or available for loading, and then other services that are useful for debugging. But so far we haven't actually mentioned the actual control loop, so here it is in its most basic form. So typically what you want to do is that you read the state from hardware, you update your controllers with the current state, which in our case is done by the controller manager, and then finally these commands that come out of the update, you send them out to hardware. So this is probably the only piece of code that we're going to be looking at. I'm going to step through a very, very simple robot setup. So this is a main function, and the first thing that you do is you initialize your ROS node, and then you create an instance of your robot. So this is what we were talking about in setting up your robot section. So by this time, robot knows about all of the resources that are available in your robot. And then what you do is you create an instance of the controller manager, and then you say, controller manager, this is my robot. Please handle those resources. And this is something that we're going to come back later on in this discussion. We set up a separate thread that is going to be responsible for servicing ROS callbacks. And then we go into what is the actual control loops. So first of all, we set up like the period of the control loop, which in this case is going to be slow, non-real time, 10 Hertz. And we do some basic bookkeeping to get the system time to compute the control period. And this is where the actual control loop takes place. So these three lines are read, update, write. And then we keep on repeating this over and over. So read, update, write. So this takes place in a thread that we call the control thread. And this thread is potentially real-time. So if your system has real-time constraints, then it is this part of the code that you should make sure that it has real-time scheduling. And as I was mentioning before, there's another thread that is called the spinner thread, which is non-real-time and is responsible for servicing ROS callbacks. So what kind of callbacks are being serviced here? So on the first place, those from the controller manager API, but then there's all the ROS APIs from your controllers, which are custom. And well, also depending on your setup, you might have other things that are registered there. This is really up to you. But the important thing here is that it's really important to have those things which are non-real time in a separate thread. And by non-real time, I'm especially talking not only about that you respect requirements from real-time applications, but also deterministic execution. So in this case, we don't have real-time constraints. It's a slow robot, it's 10 Hertz. But here it also makes sense to have these separate. Because say that you have a controller that when you load it needs to parse a URDF. And you have a URDF with, say, 10,000 joins. So there is no way to guarantee that parsing that URDF will take less than 0.1 seconds. So if you serialize everything, you put everything in the same thread, then these operations will make you not respect your deadlines in the control loop. So this is why all of those things, even if you're not using a real-time operating system, you should have them separate in a spinner thread. So because we have then two threads, they need to talk to each other. So we have to handle concurrency with care, especially with respect to the control thread, because it's real-time, so we have to make sure that we never block it, because we don't want to suffer from priority inversions or other bad things that can happen. So for this and other things, there's a package that's called real-time tools, which has tools that are usable from a hard real-time thread. And with this, you can do things like publish to a ROS topic, talk to a non-real-time thread, query estimates of the system clock. These are the kind of things that you can do with these tools. So, coming back again to the control loop, I was saying that this was probably the most basic form of the control loop, but if we stretch it up, then we can add more stuff. We're going to start by putting some placeholders here. So one thing that might happen is that you have mechanical transmissions. And if your hardware doesn't take care of them by itself, then you have to do it in software. So there's a package called transmission interface that basically implements the representation of mechanical transmissions. And what it does is that it propagates between the actuator and joint space position, velocity, and effort variables. Currently, you can use out-of-the-box reducers, 4-bar linkages, such as the one that is pictured there in the middle, and differentials. And there are plugins that help you in loading transmissions from the URDF, because otherwise it would be very complex to populate your robot hardware interfaces. So with this, the process is greatly simplified. So for a simple reducer, this is more or less what you would have to put on your URDF. I know XML is hard on the eyes, but basically what you're specifying here is the type of the transmission, the name of the actuator and joint that you are relating to one another, and things like the mechanical reduction and the type of hardware interfaces that you expect to expose. Then it should be relevant to talk about safety issues. So you might be interested in enforcing joint limits before you send your commands to hardware. So there's, as you can guess, a package that's called joint limits interface. This is the last line of defense before sending commands to hardware, and the motto here is don't trust controllers. What we implement here is simple, fast, and low-level strategies. What you can find inside this package is, first of all, data structures for representing joint limits, then convenience methods for populating these data structures, such as from the URDF or from YAML. And then there's methods for enforcing joint limits. There's joint limit, soft limit strategies, such as the ones that you can already find in the PR2, basic clampings, and they work for different hardware interfaces. I think the best way to understand this is by means of an example. So this comes from real data. This is not made up. So the blue curve there comes from a controller, is a command from a controller that we don't trust. And the red line that you see there is what happens after enforcing the joint limits. So the first thing that you can see there at the bottom is that we are enforcing the maximum velocity. And then at the top we also enforce the position limit. But because we use the sub-limit specification, then it's not a hard clamping, but it is in fact a smooth stop. Okay, and well, last issue that is also concerned with safety, there's the e-stop. So in general, the e-stop is typically very, very robot specific, so there's not much that we can do here for you. And there's also the distinction between what is an emergency stop, which is usually much harder, and you do things like to remove energy sources. But there's also the notion of a protected stop, which is meant to reduce risks, hazard control. But whatever you do, the issue remains that you have to recover from an emergency stop. So when you release the stop, what is the same thing to do? Because you have potentially many controllers running that do different things, so there is no one-size-fits-all solution on what you should do. So an interesting thing to do here is that you should let controllers decide. So the controller manager has this feature that it can be updated with an optional parameter that says controllers reset. So basically what you do here is that in a single control cycle, what you do is you take all running controllers, you stop them, you start them, and then you update. So if we adhere to the typical policy that we were discussing before, what you would do is that you stop, so you cancel all goals, you start, you enter semantic zero mode, so that when you update, you have same behavior. So with this, we conclude the part of the control loop. And in fact, we can go now into demo mode. So let's hope we don't have demo effect and the demo can work well. Okay, so there you have Ream. Ream is in gazebo. And I should also throw this here on the other screen. Okay, and that's Ream in Arbis. And I need some mouse space here. So there's my arrow. I'm going to approach a little bit here. There's our guy. And the other thing I want to do here is also to open some RQt plugins. Where's my arrow? Let's put this here. Whoa, this is really big. Okay, so the first thing I'm going to do here is that I'm going to drive the robot around. So this is the robot steering ARKit plugin, which is not from ROS Control. It's built in as one of the basic. Where's my arrow? There it is. So just to see that we can talk directly to, this is a diff drive controller that we're using here. So the robot moves, okay. Then this is from the ROS Control project. This is for the joint trajectory controller. You choose a controller manager, and then you choose one of the available controllers, and then you can simply, can you see the head moving? Oh, and this is here, this is ARKit plot, so you can also see the evolution of the trajectories. So this is really cool. So here what we're doing is basically talking directly to the controllers with a very convenient interface. Also, there's another ARKit plugin here. This is for the controller manager. So this is, you can always use the ROS interfaces and command line tools. There's some very nice command line tools for the controller manager. But you can also use this, so you can say, this is actually nice. Here's the head controller. So you can see that the joints are here. So what I'm going to do is say, please stop, and then the joints disappear. You can no longer use it. If you check here in the combo box, no head controller. But if you now say again, start, then it's here again, and then you can keep on moving your head joints. So this is the basic stuff. This is just to let you know that there's some really interesting tools that you can use for talking to controllers and changing them. But then you can do also some other stuff that is also relevant. Let me zoom in into the robot now. There it is. So here I'm raising the hands, so I'm controlling all the upper body of the robot at the same time. And what I'm going to do right now is I'm going to raise the left hand, but using Move It, so it's doing motion planning of the complete upper body. Well, it's doing like breakdancing, robot dance, and it goes up there. And just to let you know that it actually did some motion planning, I'm going to make it go back without motion planning, so that you see that it goes through itself. So there it goes, Move It bindings. And then to complete this little demo, we're going to do a narrow passage with the navigation stack. So we're going to ask the robot to come here. And it does it. So this is just to show like the basic things that you can do with ROS Control. And now I guess I should kill this to free up some resources from my machine. You're not seeing my resource monitor, but I have like 4 cores that are completely taken. Okay, so let me get back to where I was. Okay, here we are. Demo. So if the clock is good, then we have time to keep on going. So as Ryan was saying, it's really hard to estimate who's using your code or the project. So what I basically did is there's a SIG for robot control, and I wrote an email and I said, guys, if any of you is using ROS Control and you don't mind sharing some of your results, please come back to me. So this is what I got. So I'm going to proceed alphabetically. So there's the Bauman Moscow State University, which is in Russia, and they deal with space robotics based on functional model testbed. So they're using Kawasaki industrial robots, Schunk grippers, and an ATI four-stroke sensor. And it's really interesting because they're using it in combination with ROS Industrial. Then there's also Fraunhofer IPA. They're in Germany, and they deal with robots and assistive systems. They have 2 kinds of Schunk robot manipulators, and they are also using it in combination with Move It. There's at Georgia Tech, at IRIM, here in the US, they work in collaborative assembly, and they use universal robot manipulators. They also use, in combination with ROS Industrial, and then they also have this linear rail with shunt rail and inverted motor. Heidelberg is a US company that deals with contracting and technology transfer. They've been using a project based on industrial robots to make a next generation steel beam fabrication pipeline. They were dealing with plasma cutting and pick-and-place robots, and they also leveraged Move It extensively. At last, in France, the Geppetto team, their application domain is the motion of anthropomorphic systems. They are in France. They were implementing the stack of tasks, which is sort of whole body control in the PR2, and in a simulated context, they had some universal robots set up as a manipulation test bed with inverse dynamics controllers. This is where I come from, Power Robotics. We have the PMB2, which is a general purpose mobile base. It's a disk drive, so we can use it with the disk drive controller and the navigation stack. Then this is not general purpose, but actually a product. It's a robotic inventory solution. It has some RFID tags, so it also has a disk drive and uses the ROS navigation stack in stores and libraries, whatever needs inventory with RFIDs. Then we have the Ream, which is a humanoid service robot. So this guy uses Move It, joint trajectory controllers, IMU controllers, uses a lot of things. And finally we have ReamC, which is a biped research robot. It has a proprietary walking controller that is compatible with the ROS navigation stack. Okay. Then we go to Japan. There's a Tokyo Open Source Robotics Association. They have some work with the Denso industrial manipulator. They are also using ROS Industrial and Move It, so this seems to be a pretty common configuration. At the TU Darmstadt in Germany, they are in the application domain of search and rescue. They have this Dynamixel-based 3D printed arm, which has a camera at the end effector. Then there's a team, international team, made up of the joint workshop of Team Tedesar, TU Darmstadt, and TU Graz. They are also into search and rescue and manipulation, and they are using shunt manipulators to do here at least a shorting task. There it says 4x, but I actually sped it up twice, so it's 8x, so you can see more of the video. And then we also have Team Vidger, which is one of the DRC challenge competitors. They are, of course, into the domain of search and rescue, and it's made up of Torque Robotics, TU Darmstadt again, Virginia Tech, and Oregon State University. This is a work in progress for them, but they are working with the Atlas hydraulic biped robot. So what's next for ROS Control? I'm going to go real fast through this section. There's some new features that would be interesting to have. Well, I haven't mentioned, but ROS Control hasn't reached 1.0 yet. We're very careful to keep stability across ROS distributions, but so to reach 1.0, we would like there to be at least a decent library of robots and controllers that you can use out of the box, and to be also able to compose robots so that you can say, I have this mobile base, this arm, and this gripper, and have a straightforward way to putting them together. Then there's some other stuff that I'm not going to go into details here, but from a more general point of view, we would like to stabilize the APIs to reach 1.0, to have better user and developer documentation. There is already some, but we need more. And then higher test coverage everywhere, because right now we have packages that have great, spectacular coverage, but then we have some others that are not so spectacular. So since control is a very delicate thing, high coverage is important. And then, when I say ROS Control 2.0, I'm just talking about long-term vision. We would like to add things that are more for power users, so more flexibility, to have the notion of functional and data blocks, so basically to be able to chain controllers together one after the other, to lift the requirement of controllers having a periodic and serialized execution and more dynamic interfaces. So in order to do this, there's the compromise of the dependencies, because we don't want to implement all of these things from scratch. We want to build upon something that already exists. But then, at the same time, we want to keep dependencies light. And more importantly, since these are features for power users, we don't want to make the learning curve any steeper. So we have to really think how to do this the right way. we can maybe have a birds of a feather session on this, because there's a lot to discuss along these lines. So if you want to get involved with the ROS Control project, we have the code in the ROS Control's GitHub organization. There's a SIG, which is called Robot Control. And I would suggest that this should be the main channel for asking control-specific, like ROS Control-specific questions, but then there's also answers.ros.org. If you choose to go this way, please tag your questions so we can find them. And this is a list of all the people that I could find that have contributed to the project. If you have contributed and your name isn't there, I'm sorry, but I say thank you at this time. And a special thanks goes to the guys at the top, so John, Dave, and Wim. These guys have been everywhere in the code, in the discussions, and in making this presentation better. So in general, to everybody that's here, thank you so much. And then I'm going to conclude this presentation with a cool video while I take some questions from you. This is like our most recent one. Thank you so much.
We have time for questions. Well, I have one. So obviously you're using this in simulation. What has your experience been like developing controllers and tuning controllers in simulation and then going back and forth between the simulation environment?
Okay. So in our experience, there are controllers that you can use directly, like with the same configuration. Oh, sorry. The question was, we're using controllers both in simulation and with real hardware, so how different are the setups between the two? So if something changes, it's controller-specific, like gains or parameters. So depending on how good your simulation model is, then you can have the exact same configurations. In our case, what we have found is that for more dynamic controllers, such as the ones for biped walking, then we do need to tune parameters specifically for simulation, but then for things that don't take dynamics that much into account, then it is possible to use the same, like you have joint trajectory control for the upper body and you're not going to fall down, then you can use the same settings.
Talk about the hardware requirements for running this in an embedded autonomous robot.
Okay, so the question was, what are the requirements for running this in embedded systems?
Embedded autonomous.
Battery powered. Well, so all the robots that you have seen here in real videos, well, at least the ones from us, they are autonomous, battery powered, but they are not embedded. I mean, they're using i7s. But it's a great question because, in fact, the ROS embedded guys, there's an initiative where they are actually building ROS control. They're generating, they have a cross-compilation toolchain and they have ROS control there. But as far as I know, they're just doing it so that somebody can pick it up and use it. So I don't really know if somebody's using it. But I would say ROS control is implemented, it's C++, and it uses ROS. So whatever you use, it should be able to support that. So if you have a compiler that supports C++ and also can build ROS and provide ROS, then you're good to go. Yes?
Just as a follow-on to his, have you done any profiling? You said you're using i7, so have you done any profiling in terms of like memory, CPU usage, things like that? Like how much of the i7 are you using?
Well, we're never using more than one core, but in the end, what ROS control is a lot of infrastructure and bookkeeping, but the actual computation is what you put in the controllers. So ROS control in itself, it's not using resources. So if you have lightweight controllers, then you can put that in a small robot, but if you have really hardcore controllers that are running dynamics and at a very high frequency, then you're probably going to need a bigger CPU.
And with that, we're going to have to wrap it up. So thank you, Adolfo.
Okay.